Imagine you're that brilliant, slightly caffeine-addicted AI researcher, right? You've poured your heart, your soul, maybe too much coffee, into training your new agent aide. You're running it on this killer benchmark, MLE-bench. You hold your breath, maybe cross your fingers, and it gets, okay, a 39.6% medal rate. Decent, I guess, but you know it can do better.
And that feeling, that initial kind of frustration, it's often the catalyst, isn't it? It forces a deeper look. Instead of just pushing harder with the same tools, you start wondering maybe the tools themselves are the issue. It opens up completely new lines of thought.
Exactly. So it hits you, these research agents, they're basically just fancy search algorithms plus a bunch of, well, tools. Operators, they call them, like digital wrenches and screwdrivers for tweaking code. You start picturing these graphs of code, nodes, and edges, thinking, yeah, draft, debug, improve, we're transforming things. It feels like progress. So you throw the kitchen sink at it, every sophisticated search strategy, Monte Carlo tree search, evolutionary algorithms, the works, and nothing, like zip, zero gain. Turns out, your wrenches were rusty. It wasn't the search strategy after all. The operators were the bottleneck. Sound familiar?
That's such a critical insight, isn't it?
Yeah.
It reveals this fundamental constraint. Even the smartest search strategies, the most advanced algorithms, they're completely limited by the quality, the actual capability of the operations they can perform. If the tools aren't good enough, the strategy just stalls.
Right. And that's the big aha moment. So you go back to the drawing board. You have to redesign those operators from the ground up. You give them cool new features, scoped memory so they remember the right things, adaptive complexity so they don't overcomplicate things too early, even think tokens, basically. You teach them to think better, not just, blindly operate. And then the magic happens. You pair these new super smart operators with your search strategies, even just the simple greedy one to start, and boom. Your new system, let's call it AIRA, it jumps way up. Suddenly you're seeing like 47.7% medal rate. Okay, now you're feeling pretty good, right?
That's a significant leap, a really big jump. And it directly validates that hypothesis. The operators really were the key constraint holding things back.
But then you look closer. You check the validation results, and you get that sinking feeling. You know the saying in the trenches, right? Validation lies, test tells the truth. You start thinking, hang on, what if I just pick the final solution based on the test score instead of the validation score? And bam, suddenly it's another, 9 to 13% more medals, just from picking the winner differently. Crazy. Then you add this virtual training dojo, AIRA dojo, proper sandbox environments, apptainer isolation, all the good stuff, and the original aid agent. Just by running in this better environment, it gets 10% better. Just from the setup, you push the training longer, 24 hours, than 5 days. And Area A, the new system, it keeps climbing. It kind of stalls out. You even see the strategies learning from each other. MCTS starts benefiting from insights the simpler, greedy search found. And the evolutionary approach. It's borrowing ideas from both.
And what that really demonstrates is a maturation of the whole system, wouldn't you say? It's not just the individual components getting better in isolation.
Yes.
It's how they interact, how they work together within this robust environment, especially over longer time horizons. That's where the synergy really starts to kick in.
And then it really clicks. The ultimate realization, this isn't just about writing lines of code, is it? ML research, it's not just code. It's search over abstractions. It's figuring out what to try, how to tweak things conceptually. So when someone comes along and says, oh, but it's just operators, you can calmly pull up those search trees. Look, here's MCTS exploring broadly. Here's evolutionary recombining promising ideas. Here's greedy just honing in. And look how together they smoke any single one alone. And maybe they push back, okay, but 47.7% isn't perfect. And you just point to that test validation gap, say, fix that overfitting issue and watch the numbers climb higher. Usually they go quiet then, and then it hits you. You didn't just train some agent to win a Kaggle competition. You actually trained, well, the scientific method itself in code.
That really elevates the whole conversation, doesn't it? If we can actually encapsulate the core scientific method hypothesis, experiment, refinement into an automated agent, what does that mean for the future? The pace and the very nature of discovery, not just in ML, but across all sorts of scientific fields. It feels like a paradigm shift, moving from automating tasks to automating, inquiry itself.
Absolutely. Welcome, everyone, to The Deep Dive. We're here to extract the most important, most interesting nuggets of knowledge from the sources you share with us. Today, yeah, we're plunging deep into this fascinating world of AI research agents, how they're starting to automate scientific discovery, specifically within machine learning. We're looking at some really cool cutting-edge research. This comes from folks at Meta, University College London, and Örebro University. And we're focusing on how these digital scientists are built, the tools they use, those operators we talked about, and, crucially, the surprising challenges they bump up against. Our mission today, to really show you how this interplay between an agent's tools, its operators, and its strategies, its search policies, how absolutely critical that relationship is for making breakthroughs in this new era of automated research.
Precisely. And just to ground us, at its core, what is an AI research agent? It's essentially an autonomous system. Its goal is to speed up scientific progress, specifically by automating the tricky parts.
Right.
Designing models, implementing them, training them, iterating. You can think of them as navigating this huge, almost infinite space of potential solutions, trying things out, tweaking them, and constantly evaluating how well they're doing.
Yeah, and the way they formalize it, the way they structure this thinking is actually quite neat. They basically treat these agents as sophisticated search algorithms operating on what they call a directed graph. So imagine a map. Each point on the map, each node is a possible solution, maybe a chunk of code or a specific model setup. They call these artifacts. And the paths connecting these points, the edges on the graph, those represent the transformations, how you get from one potential solution to the next, by drafting, debugging, improving.
Exactly. And within that formal structure, there are really 5 key components that define how these digital scientists work. First, you need a fitness function. That's how the agent estimates how good is this solution. Often it's a proxy, like 5-fold cross-validation score. Not perfect, as we'll see, but necessary. Second, there's a selection policy. Which existing solutions should the agent focus on next? Where does it decide to spend its effort? Third is the operator set. That's the toolbox we mentioned. All the possible actions: draft new code, debug existing code, improve something, maybe even crossover, combining ideas. Fourth, the operator policy. Okay, you've chosen where to work. Now which specific tool do you use? Draft, debug, improve. And finally, fifth, there's the termination rule. When does the agent stop searching? Maybe it runs out of time, hits a compute budget, or reaches some performance target.
Okay, so you've got these agents, these digital scientists, all formalized. They need a place to actually test their mettle, right? A proving ground. And that's where MLE-bench comes in the machine learning engineering benchmark. This thing is tough. It's built from real tasks taken from Kaggle competitions. The full benchmark has 75 tasks, which is huge. For this particular study, they used a elite version with 22 tasks, still very challenging. And the goal: for the agents to own metals bronze, silver, or gold, just like human competitors would. It's designed to be a real-world testbed for AI and ML engineering.
So let's talk about the baseline they started with. Before ARA, the state-of-the-art agent was called AID. That stands for AI-driven exploration in the space of code. And AID, its core design, was basically a greedy search algorithm. What that means is at every step, it would look at its current best solution and apply one of its operators: draft, debug, or improve, trying to make the immediate best improvement possible. Always focused on the local optima.
Right, the standard greedy approach. So the researchers did the obvious next step, didn't they? They took AID with its original operators, mathematical sextaid, and they paired it up with those more advanced search policies we talked about: Monte Carlo tree search, MCTS, evolutionary search. The strategies that should, in theory, be much better at avoiding local optima than plain greedy search. The expectation, naturally, was that these fancier strategies would unlock better performance, right? That seemed like the logical path forward.
That's exactly where the big surprise happened. Despite using these much more sophisticated search algorithms, there was basically no significant gain in performance. The metal rates were all clustered together, barely any difference. And this was the critical moment, the bottleneck insight. It strongly suggested that the limitation wasn't the search strategy, it was AID's operators. The tools themselves were holding back the smarter strategies, a really fundamental finding.
Such a cool moment in research when the obvious turns out to be wrong. And that insight leads us straight to ARA, the intelligent response to that operator bottleneck. So based on that finding, the researchers didn't just tweak AID's operators. They went back and designed a fundamentally improved set of operators, which they called Magka. They really rethought how these tools should work at a deeper level.
They absolutely did. One of the key innovations was this idea of prompt adaptive complexity. This is really clever. Essentially, the operators, especially draft and improve, dynamically adjust how complex the code or solution they generate is. So if the search hasn't explored much down a certain path, maybe fewer than 2 child nodes, it generates a simpler, minimal artifact. But if there's been a lot of exploration, say 5 or more children, it generates a more advanced, complex artifact. It stops the agent from over-engineering too early, starting simple and getting complex only when needed. Very efficient.
That makes a lot of sense. And they also tackled memory, right, with the scoped memory idea, which sounds much better than just giving the AI everything it ever knew.
Yeah, instead of just a big memory dump, the memory operator got way smarter. For draft and improve, it specifically retrieves sibling memories. So it looks at other attempts made from the same parent node. This helps promote diversity, stops the agent getting stuck in one rut, avoids overloading it with irrelevant context. But for debugging, crucially, it retrieves ancestral memory. It looks back at previous attempts to fix that same code lineage. This helps prevent those awful undo-redo loops where it keeps trying the same failed fix over and over. It's so smart.
And building on that idea of smarter internal processing, they introduced think tokens. This wasn't about changing the output code itself. Instead, the system prompts for the operators explicitly encourage the underlying large language models, the LLMs, doing the work to use structured reasoning, to kind of think out loud internally. These internal thoughts, the reasoning steps, were then stripped out before the final answer was generated, so they didn't clutter the actual code. But the effect was significant. They observed a 2 times increase in the number of completion tokens used by the LLM. It suggests much deeper internal processing was happening, leading to more reasoned outputs.
Wow, so it's actually doing more work internally. And then for the evolutionary strategies, they added a completely new tool to the box. Crossover. Makes sense, right? Just like in biology. This operator takes 2 existing solutions, 2 artifacts, and tries to recombine the useful bits from both to create a new hybrid solution. It's perfect for evolutionary algorithms, letting them effectively blend successful ideas from different parts of the search space.
Okay, so now they have these much sharper tools, the enhanced ARA operators, math call STIRS. The next step was crucial. Prove their impact. So first, they did a direct comparison. AR greedy, that's the new ARA operators, combined with the simple greedy search versus ADA greedy, the original 8 operators with greedy search. This setup perfectly isolated the effect of the operators themselves. Same search strategy, different tools.
And the result? Pretty clear cut, wasn't it? AR greedy just blew ADA greedy out of the water. It got a 45.5% metal rate compared to AID's 39.8%. That's a 14% relative improvement just from changing the operators. It totally confirmed their hypothesis. Better tools really were the key.
And then here's the payoff. With those enhanced ARA operators finally in place, the advanced search policies, ARA Monte Carlo tree search, and ARA-IVO, evolutionary search, they finally started showing significant performance gains over the greedy approach. They weren't being held back anymore. The smarter strategies could actually leverage their strengths because the underlying operators were capable enough.
Right, which led to the new state-of-the-art performance on the benchmark. AI ramps, using the DeepSeek R1 model, hit that 47% average metal rate on MLE-bench Lite. Pretty impressive. And another really interesting point they noted, the performance differences between AR-greedy, ARIAMS, and AR-EVO didn't really become clear right away. Meaningful divergence where you could really see MCTS and EVO pulling ahead only started appearing after about 19 hours of computation. It really underscores that for these complex agent systems, you often need those longer runs to truly see which strategies excel. Short runs can be misleading.
Okay, but let's pivot to another huge challenge in this space, something that affects pretty much all ML development, that tricky generalization gap. This is the core problem. The agents are making decisions, guiding their search, based on validation scores. These are calculated on a subset of data. They're just a proxy for real performance. But ultimate success, the thing we really care about, is measured on a completely unseen, held-out test set. And that gap, that discrepancy between the validation score the agent sees and the true test score, that can lead the agent astray, causing it to overfit systematically to the validation set. It thinks it's doing great, but it's just memorized the wrong patterns.
Yeah, the classic overfitting problem. So they tried to quantify how big a deal this gap actually is. They asked, okay, hypothetically, what if the agent could use the true test score for everything guiding its search, picking the final answer? The results were kind of eye-opening. Performance would jump by, depending on the agent, somewhere between 9% and 16.6% in absolute metal rate. That's huge. It just shows how much potential performance is being left on the table because the agents are optimizing for a noisy, imperfect proxy metric.
And what's really insightful is where a lot of that gap comes from. They found that a huge chunk of it, roughly 9 to 11.6 absolute percentage points, was just down to the final selection of the solution. Meaning, even if the search itself was guided by the potentially noisy validation scores, if you simply went back at the very end and picked the best node from the entire search history based on its test score, you recovered a massive amount of that lost performance. For the greedy agents, it closed over 60% of the gap. For MCTS and evolutionary agents, it actually eliminated the gap almost entirely in their tests.
Wow, so just picking the winner more wisely at the end makes a massive difference. That suggests a pretty practical fix, right?
Exactly. They proposed a simple mitigation. Just hedge against validation score noise. Don't just pick the single top solution based on validation. Instead, select multiple promising candidates, say, the top K ranked by validation score, maybe the top 3 or top 5. Then you evaluate those few candidates on the test set and report the best one. They found that using as few as just 3 top K submissions could claw back an extra 10% in performance on average. It's a straightforward way to get closer to that true potential.
Now, we've spent a lot of time on the algorithms, the search policies, the operators, the brains of the operation. But there's another piece of the puzzle that turned out to be incredibly important, kind of an unsung hero. The environment itself, specifically the ARA dojo. This research really highlights that it's not just about the algorithms. The whole ecosystem they run in matters a lot. Oh, totally. The impact was actually kind of stunning. They took the original baseline 8 agent, no changes to its algorithms or operators, and just ran it inside this new ARA dojo environment. Compared to its previously reported results, its medal rate jumped from 35.2% all the way up to 45.9%. That's a 30% relative improvement just from the environment. That's massive.
It really is. So what makes AI Dojo so special? Well, it's designed to be a scalable and customizable framework. It provides a really robust way to interface with compute resources. A key feature is its use of Abtainer containers. This gives complete isolation for each agent run. It stops agents from messing with the host system or interfering with each other, which is critical for reproducibility and stability. It also provides agents with root-like privileges inside their container, which they often need to install packages or configure things. And includes a super image, a pre-built container image with common ML tools like PyTorch, TensorFlow already set up, saving time and ensuring consistency.
Yeah, and the design clearly came from battling real-world engineering headaches. They explicitly designed it to handle things like hitting rate limits on external LLM APIs, which push them towards self-hosting the LLMs for reliable scaling. They tackled the common problem of agents accidentally corrupting their Python environments. Virtualization solves that by giving each run a clean slate. And they built in robust checkpointing to handle the inevitable hardware or software failures you get in large-scale experiments. It just highlights how much heavy lifting, pure engineering effort goes into making this kind of AI research actually work at scale. Infrastructure is definitely not an afterthought here.
Which brings us nicely to the long game, scaling these systems up and looking towards future frontiers. Most benchmarks, including MLE-bench, have these fixed time limits, often 24 hours. But what happens if you let them run longer?
Right. So they did experiments pushing the runtime way beyond 24 hours, up to 90, even 120 hours. And the results were interesting. The ARA agents, with their better operators, they kept improving during these extended runs. They continued to find better solutions. The older aid greedy agent, however, tended to plateau much earlier. It suggests that for really complex problems, more compute and longer runs can yield better results with these improved agents. But there's a catch. Over those very long horizons, that generalization gap we talked about, it becomes an even bigger problem. Even the advanced ARA agents eventually started to systematically overfit to the validation data when run for extremely long periods. It seems to be a fundamental limitation right now.
So looking ahead, what's next for these AI research agents? Where does the field go from here?
There are several exciting directions. One idea is exploring agentic operators. Instead of operators being relatively simple functions, imagine using entire specialized AI agents as operators within the larger search framework. Like you could have an ideation agent operator or a debugging agent based on something like SWE agent, a team of agents, essentially. Ooh, that's meta. Agents calling agents. Yeah, I like it. What else? Well, there's obviously fine-tuning the LLMs, making the underlying language models that power the operators even better at these specific tasks, maybe through supervised fine-tuning on successful code transformations, or even using reinforcement learning to reward good operator outcomes. And then there's the perennial challenge of just scaling the search. How do you design agents that can effectively use vastly more compute orders of magnitude more over even longer time horizons? That's a huge open question for tackling truly grand challenge problems.
Another really critical challenge they raise is data contamination. As these powerful LLMs are trained on more and more internet data, including potentially coding competition sites or academic papers, there's a growing risk that they might have already seen solutions or new solutions to benchmark tasks during their own training. This could artificially inflate performance and make evaluations unreliable. So figuring out how to create a continuous stream of genuinely fresh, novel tasks for benchmarks is becoming a really important area of research itself. We need truly unseen problems to measure progress accurately.
Yeah, that's a tough one. And related to reliable evaluation, they make a strong practical recommendation based on their own experience with variance. They strongly suggest researchers use a minimum of 10 random seeds per task, and ideally even 20 when evaluating these agents. The performance can just be inherently noisy, run-to-run variance is high. Using more seeds gives you much more confidence that your results and rankings are robust and not just down to luck. Good experimental hygiene, basically.
Okay, so wrapping this all up, what are the key takeaways for you, the listener? This deep dive, I think, really shows that automating scientific discovery with AI, it's not just about having the biggest model or the fanciest algorithm. It's a much more meticulous process. It involves actually formalizing the scientific method itself, hypothesis, experiment analysis, into code into these agent frameworks. It's about that crucial step of recognizing when your fundamental tools, your operators, are the bottleneck holding you back. It's about the constant refinement of those tools, and then smartly applying the dancer strategies. And finally, it's about being really honest, brutally honest sometimes, about that generalization gap, the difference between your validation metrics and true real-world performance.
Yeah, absolutely. And if we zoom out one last time, connecting this to the bigger picture, the progress we're seeing in these AI research agents, it suggests the very engine of science, that cycle of hypothesis, experiment, refinement, is itself becoming increasingly automatable, which leads to a really profound question, I think. As AI gets better and better at being a scientist, maybe even surpassing human capabilities in certain complex domains, what completely new frontiers of knowledge might it unlock? What kinds of discoveries are out there waiting to be made, perhaps not by human intuition alone, but by the relentless, systematic exploration of the scientific method executed in code? Something to think about.